This is the 24th lecture of EP1. In this lecture, what we will do is we will start looking into the composition of objects. So far we have talked about motion mostly. We talked about objects moving. Objects were extended bodies. We would like now to zoom in and see under the hood what they are made of. So we all know that if you really zoom into objects, you will see that all of them are made of atoms and molecules. This is a very ancient idea, and it's very surprising that this idea wasn't fully embraced by all the scientists until the beginning of 20th century. So in the beginning of 20th century, there were serious legitimate physicists and chemists who still doubted the existence of atoms and molecules. Today, we know that that's a matter of scientific fact. There are atoms and molecules. One thing that we often don't appreciate is how many atoms and molecules are really in there. These objects are really tiny. So if you take a grain of sand contains on average 40 quintillion atoms. And that's a really huge number. Those atoms and molecules, they're not just sitting there, they're moving around. Exactly how they move around depends on what kind of object you have. If you have solids, then in most solids, you have those atoms arranged in a regular mesh-like structure. That's why solids preserve their shape and volume. These atoms, however, are not fully, they're not motionless. They make small vibrations around their equilibrium positions. In the liquids, things are different. In liquids, you break the bonds between molecules, and you have those molecules. Now they can move with respect to each other, but there isn't a lot of space in between them. So liquids can change their shapes, but cannot change their volumes easily. And then we have gases. When you have gases, you have atoms, and there is quite a lot of space between atoms and molecules. So gases, they don't preserve. They don't preserve either their shape nor their volume. And so in gases, these molecules move pretty fast. They are free to move around. In liquids, you also have motions. In solids, you have vibrations. And that motion of molecules that make up objects is what our bodies perceive as temperature. When we touch something, and when this thing feels hot to touch, that means that there is a lot of vibration going on inside that object, and these molecules collide with the molecules in our hand. They make molecules of our hand vibrate faster, and our brain perceives it as high temperature. Temperature is something that we all have some familiarity with from everyday life. You can measure temperature with one number. So it's not a vector, it's just a scalar, just one number. There are many different scales for measuring temperature. There is centigrades. In the centigrade scale, Celsius scale, you fix the temperature of melting ice to be 0 degrees, the temperature of boiling water to be 100 degrees, and then divide this range into 100 equal steps. Then there is Fahrenheit, widely used in the United States. You are probably all familiar with the Fahrenheit scale. For reasons that will become obvious later, physicists really like Kelvin scale. This Kelvin scale is named after a great 19th century British physicist, Lord Kelvin. And the idea behind Kelvin scale is that there is a minimum of temperature. So if you think about this, if temperature really is the energy of molecular motion, then there is bound to be a minimum temperature because the molecules can move faster, but there is a lower bound on how fast they can move. That lower bound is 0. So there is this high temperature, hypothetical temperature that cannot really be reached in labs where all molecules stop. And that's what Kelvin scale takes as 0 degrees. So 0 degrees in Kelvin scale is the least temperature that you could get. And then 1 degree Kelvin is the same as 1 degree centigrade. In the Kelvin scale, the room temperature happens to be at around 300 degrees. And if you look into your textbook, you will find conversion between centigrade, Fahrenheit, and Kelvin temperature scales. So it's reasonably straightforward. I don't want to spend a lot of time on it, but if in your homework you have to make this conversion, just look it up online or in your textbook. So we will start exploring this subject of internal structure of objects and their thermal motion. We will start by looking at simple things. For example, how does the change of temperature affect things? So first, one thing that I should probably mention before we move further is that in the first 13 weeks of EP1, when we would talk about friction, we would say that friction is a non-conservative force and that friction takes away energy from objects. So it is true in some sense, but in some other sense it isn't true. So what's happening with friction is that if you remember this mental picture of friction that we had, when two surfaces touch, there are always some imperfections, and those imperfections rub against each other, and that causes friction. So what's happening here is that you have atoms and molecules of those two surfaces, and because of the friction, those atoms and molecules start moving faster, and that's where the lost energy is going. So when an object loses its kinetic energy, as a result, you always have increase in this internal energy of atoms and molecules in the neighborhood. And if you were able to compute the energy that the atoms and molecules gained, you would see that the total energy is in fact conserved. So kinetic energy plus potential energy plus internal energy, let's call this internal energy, where internal energy is the motion of the energy associated with the motion of molecules. This entire thing is always conserved. The reason we introduce, the reason we say that friction is non-conservative is that this internal energy is kind of messy to deal with. It's not as nice as kinetic and potential energies. So sometimes it's convenient to take this point of view, especially in mechanics, where you have your mechanical energy, and then you call this part lost energy. So anyway, let's move to the effect of temperature change on solids. Let's say I have a solid bar. I will draw atoms, not to scale, obviously. So we know that when temperature increases, those atoms move faster, vibrate faster. The vibration now has larger amplitude. And the overall effect of this is that those atoms or molecules, they will on average move further away from each other. They will be pushing on each other more. There will be more space in between them, and the overall effect is that this bar will become longer if you heat it. So this is low temperature, this is high temperature. Under usual circumstances, when temperature increases, solids get bigger. The formula for this is that the change in length is equal to the original length times the change in temperature times the coefficient of thermal expansion. So let's look at this formula. Let's see what it means. So basically, what this formula tells you is that longer objects will get more delta L. The more you increase temperature, the more change in length you get. And the meaning of this alpha is that it's kind of like a density. It's a property of a material. Different materials have different coefficients. High coefficient means that that material expands really well under temperature changes. Low alpha would mean that the material doesn't expand that much. So the alpha has numeric values of order of 10 to the minus 6. And the specific values for different substances like aluminum, copper, steel, wood, you can find in tables. There is a table in your textbook. You can also Google it. So this is kind of like a moment of inertia or kind of like density. This is something that we will look up when we need to. So I'm now on slide number 4. On slide number 4, we have I have 2 questions that we like to ask our students. They are kind of tricky questions. So one question is, let's say you have this square made of metal, and there is a hole, circular hole in the square. The question is, if I heat up this square, what will happen to the hole? Will it increase in size or will it decrease in size? So why don't you pause this video, think about it, and then get back to the video. Okay, so the question is, what happens to this hole? Will it get bigger or smaller if I heat up this square? And you could argue for both, you know, since everything is, since this metal expands, you know, depending on how you look at it, you may think that the hole is getting smaller. What's happening in fact is that the hole is getting bigger, and to understand why the hole is getting bigger, let me make this hole, instead of being circle shaped, let me make it square shaped. So let's say I have this big square, and on this big square, let's say I have a smaller square cut out. So this is cut out. And now what I will do is I will divide this donut into 1, 2, 3, 8 imaginary smaller squares. And I will think about what happens to each square as I heat up this metal. It's obvious that each square gets bigger. So this square will get bigger, this square will get bigger, this square will get bigger. And if I make those squares bigger, and if I draw my object, I will see that this disk, this plate became bigger, and the hole in this plate will also become bigger. So bars become longer, cuboids become larger in volume, and if you have a hole in a solid, that hole also becomes bigger with them as temperature increases. So the second question isn't tricky. I don't think it's tricky. So the second question is about a bimetallic strip. So you have a narrow strip of brass on top, and then you have steel on the bottom. And the question is, if I heat this up, let's say I put some fire here. If I heat it up, what will happen to this bimetallic strip? Will it stay straight? Will it bend up, or will it bend down? So why don't you look up the coefficient of thermal expansion of brass and steel, and think about this and get back to the video. Okay, so I checked this, and turns out brass has a coefficient of expansion of roughly 19, 10 to the minus 6, and that steel has the coefficient of expansion of roughly 13, 10 to the minus 6. So if you subject them to the same change in temperature, brass will expand more than steel. Brass will expand more than steel. They are glued together over here, so the endpoints have to stay together. And now you have to think about this. Now you have to imagine geometrically what's happening. If brass is longer than the steel, and if the endpoints are fixed, then to make this work, this strip will have to bend down like so. So this is brass, this is steel. This is for high temperature. If you do the opposite, if you cool it down, then the bending will happen in the opposite direction. It will bend upwards. What's happening at low temperatures. Thermal expansion is not that large of an effect. You can see that these numbers are small. So what does this number mean? Let's take brass, for example. The coefficient of thermal expansion of brass is 19, 10 to the negative 6. What does that mean? That means that if I have, so this is the formula. It means that if I take a 1 meter stick of brass, and if I change my temperature by 1 degree, okay, then this 1 meter stick of brass will become 1.00019. Yeah, 19 meters. So that's not a big deal. If I increase my temperature by 20 degrees, then I have to multiply this by 20, so I will get 1.0003838 meters. So again, it's not a big deal. But it does sometimes become a big deal. For example, if your length is big to start with, then the same fractional change in this length will now be a big number. So for example, if I have a brass rod that's 100 meters long, and if I heat it up by 20 degrees, then 100 by 20 times 19 times 10 to the minus 6 is, what is it, 2,000, 38,000 times 10 to the minus 6, 1, 2, 3, 4, 5. Yeah, it's still a small number, but now it's kind of, even though it's still a small number, it's like it's almost 4 centimeters. And 4 centimeters, that's about 2 inches. You know, in absolute terms, that's not a small small expansion. And that's the reason, for example, why bridges have expansion joints. Those expansion joints are in there because when it's summer and when the metal expands, you don't want things breaking. You want there to be a gap that will allow things to expand without breaking anything. Okay, so this was thermal expansion. Again, the key formula is that your expansion is the length times change in temperature times alpha, where alpha is a number you have to look up in tables. And there are a few homework problems on this. So in one of the homework problems, what you have to do is you have, sorry, let me quickly look this up. You have you have a rod, and you have a ruler. you put this rod and the ruler, you put them both in the oven, you heat them up, and then you have to measure the length of the rod. And basically the question is, they ask you for the coefficient of thermal expansion of this rod. And so the thing to keep in mind here is that if you heat up both the rod and the ruler, both of them will become longer. But they're not gonna become longer by the same amount. So the reading here on the ruler will change. There is question 2, which is also about the expansion. In question 2, you have a steel rod. And you have a brass ring that looks like this. And the size of this rod and the size of the opening in this ring are roughly of the same size. The rod is made of steel, and this ring is made of brass. The question is, at what temperature will you be able to slide the ring onto the rod? And again, you have to keep in mind that brass and steel have different coefficients of friction. Brass expands more than steel. So at low temperatures, this brass ring would be smaller. At high temperatures, this brass ring would be much wider than the steel rod. And you have to find this perfect temperature where they are of the same size. So this, I think, is, as a concept, is pretty simple, and the formula is also very simple. If you have any questions, please join the Zoom help room on Mondays, Wednesdays, and Fridays. So what I want to talk about next is how the thermal energy is transferred between objects. But before we do that, before we talk about the details, I want to consider in general, I want to look at an object, and I want to see what happens to this object if I add heat to it, or if I remove heat to it somehow. So it doesn't matter at this point how we do that, but we add heat and we remove heat. So how does the amount of thermal energy that goes in and goes out relate to the temperature of this object? Now, it's clear that when you add energy, the temperature must go up. And when you remove energy, the temperature must go down. So there must be some sort of proportional relationship between the energy that you put in and the temperature increase. And the exact formula turns out to be pretty simple. The formula is that if we write Q for the heat, and if we write delta T for temperature, for the change of temperature, then Q is indeed proportional to delta T. There is also mass in here, and there is this coefficient C called specific heat that we will talk about in a second. So let's look at this formula. We have heat equal to specific heat times mass times temperature, change in temperature, and let's see let's decipher this formula. Let's see what it means. So I think the meaning of this temperature is, meaning of this formula should be more or less clear. You have Q here, you have delta T here. So this tells you that if you add more heat, if this is positive, then your temperature will change more. If you remove heat, if this is negative, then your temperature change will also be negative. The meaning of the mass here is that if you add some amount of heat, let's say 500 joules of heat to two objects. So to two objects, object A weighs 10 kilos and object B weighs 10 100 kilos. So if I add the same amount of heat or thermal energy to a lighter object and to a heavier object, the lighter object will see a larger increase in temperature than the heavier object. So the C times 10 times delta T has to be the same number, 500 in both cases. If mass is high, then temperature has to be low. If mass is low, temperature has to be high. And that kind of makes sense. I have something small here, I have something big. If I give them the same amount of heat, it will have a proportionately large effect on the small object and a smaller effect on the large object. So that's the mass. Now, let's get back to this coefficient, this specific heat. C. C is basically a number like alpha, like density, that describes different substances. So if you take 1 kilo of water and 1 kilo of wood and 1 kilo of iron, and if you give all of them a certain amount of energy, let's say 100 joules to all of them, then those substances, for reasons that are kind of complicated, will not see the same increase in temperature. Some substances, for some substances, it's really easy to make their temperature go up, and for some substances, it takes a lot of heat to change their temperature. And this coefficient of specific heat describes precisely that. High coefficient of specific heat tells you that you need to put a lot of thermal energy into an object to make it its temperature change, and low specific heat tells you that it doesn't really take that much thermal energy to make this substance change its temperature. Water has a specific heat of 4,200 joules per kilo per degree. So this is a pretty high number. If you have 1 kilo of water and if you want to change its temperature by 1 degree, you need 4,200 joules of energy. For comparison, the iron has a specific heat of 450 joules per kilogram per degree, which means that to change the temperature of 1 kilo of iron by 1 degree, you only need 450 joules of energy, about 1/10. So given equal circumstances, the temperature in iron of an object made of iron will increase, will be higher compared to the temperature of the same amount of water if you transfer the same amount of heat, thermal energy to them. So I will stop here. This is first half of lecture 24, and in the second half I will expand on this concept of absorption and release of heat, and I will solve a few problems for you from the textbook.